we're going to look at plane waves at discontinuities. And so in this situation, we have a transition between a material 1 and a material 2. Material 1, very simple materials, characterized by 3 numbers. What are those 3 numbers? Perfect. Sigma 1, which is the conductivity, epsilon 1, dielectric constant, and mu 1, the permeability, the magnetic part of it. And then in material 2, the same set of numbers, different values. And the distinction between these, there's my z-axis, and in class we always do the simplest cases. Your homework problems are harder, so we're going to just be able to put that discontinuity at z equals 0. Okay? It makes our math a lot easier. We don't have to carry around a little offset. Things will have parity and things like that will be much nicer. This transition, I want to talk a little bit about this transition. And I want to do so in the context of something we talked about a couple of classes ago, which part of the dispersion relationship in a particular material. Okay? And we found that lambda nu is equal to c, or lambda f is equal to the speed of light. And so I remember I said that this wavelength was kind of the ruler that the plane wave carries around. Okay? So I want to ask a little bit about the step function behavior that we have right at z equals 0. How sharp a transition should that be in real life? In real life, do we ever have a step function? No, it's a mathematical idealization. So what about this ramp? What about this rise time or this ramp time on that transition? How fast does that have to be? Does it matter what frequency we're at? Do things look shiny and smooth at one frequency and not at another frequency? Yeah. Yeah, if you look at IR pictures, things that look sharp and featured in the visible become smooth and blurry in the IR. For example, the hair. The hair will just be a smooth blob if you even see it at all. Whereas in the visible, we can see the fine structure of our hair. When hair comes up on end and stuff like that, all that stuff gets smoothed out. And so the transition here depends on where we're looking at it. And in fact, I can tell a little bit about optics that you actually specify 2 parts of this, of how smooth that transition is, in terms of specs that are related to the fundamental unit of the wave, which is the wavelength. Okay, so the wavelength is sort of the ruler that the wave carries along with it to look at, to see whether or not it can discern these imperfections. And so a good optical, there's 2 pieces here. One is how flat the rise time on that thing is. And that's, a good optical surface is planar to about 1/10 of a wavelength. Okay? And so that's how you might specify how flat that surface is. But that doesn't take into account any ripples or any imperfections on that surface. Okay? And so in the optics world, you specify that with a specification called a scratch and a dig. And they specify the rough size of those scratches and the digs in that surface. And a standard optical quality scratch and dig is 60/40, which is loosely tied to the number of nanometers of the average scratch and the average dig. But where do the scratches and digs come from? Well, how many of you have ever sanded wood? So when you sand wood, describe the process.
Put a sander to it, have to smooth it out, otherwise you get the little bumps and all of that.
So just pick up a piece of sandpaper and start sanding it, right?
Yeah, but it has to be the right sandpaper.
The right sandpaper.
Yeah.
Is there? How do you pick the right sandpaper?
The texture of the numbers it's given.
Okay. So only one. When you go to the hardware store, you buy. You know what number to buy, and you buy the one number that is right.
No, I've gotten several different ones to do several different sandings, just not like one particular one.
So one piece of wood, would you use several different types of sandpaper on it?
Depending on the wood.
I would. I would start with a coarse sandpaper. If it depends, you're right. Depends on how fine the state of the wood that you get in, right?
Yeah.
But you were nodding your head. How do you do it?
Well, you start with the coarse one and then work down to a finer sandpaper.
Why? How come you don't just do the finer sandpaper?
Well, if you start with the fine, it won't smooth out some of the bigger imperfections that you might want to get rid of.
And why do you even use the fine stuff at all?
Because the coarse one won't get the finer imperfection.
Okay. So the other way to think about it, right, is you have a piece of block that is wiggly, and you come in with a coarse sandpaper. If you looked carefully in our magnifying glass, you'd see the coarseness. You'd see the grit, the trails of the grit on the coarse, right? And so you use the rough one to get yourself close, and then the fine one erases. It actually goes back and erases the damage that you did to the surface with the coarse one, right? And so that's why the order. That's why you need both the coarse and the fine. And so if you think in terms of this, there's still imperfections after you do the fine one, but the imperfections, the scratches and the digs on that piece of wood, is related to the last or the finest sandpaper that you use. And so when you specify in an optics world, when you specify that scratch and dig characterization, you want it small relative to the wavelength that you're working at, and that tells the lens polisher what grit to put in their slurries. Okay, so what they'll have is a big vat of fluid with suspensions of particles in it, like sandpaper. And they'll flush it through the system, and they'll grind, and that slurry gets recycled and goes back through it and stuff. It's a very strange thing to watch. Okay, but I say this because the specification of that surface is specifically described to the wavelength at which you're going to be working, or the frequency at which you're going to be working. And so by extension, you can say, well, if I want this to be within a wavelength over 10, 1 part in 10, then you can back that out and look at what a smooth surface is at any frequency of plane wave. So, if you're working at a gigahertz, the wavelength is a foot a nanosecond, a gigahertz. That's kind of my mantra. And if you think about the surface of this wall, do you see how it has a blotch on it? I think they call it an orange peel kind of a surface. They've mixed junk in with the paint to give it that texture. That texture is obvious in the visible world, but to a 1 gigahertz signal, it'd be nothing. There'd be no difference. It could not. The wavelength couldn't resolve the surface roughness of the orange peel of the walls. or the texture of the fabric on the floor, or even if there was fabric on the floor. And think about, the question is a shag rug a smooth interface? Is a shag rug carpet a discontinuity, a smooth discontinuity? And it certainly would be at a gigahertz or lower, and probably not at a gigahertz or higher. Okay, so this thinking a little bit about the practicabilities of what this step function is, just kind of tells you what problem we're kind of solving. If I have a metal surface, and I'm trying to build a metal mirror for the optical world, I've got to polish that very, 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 very fine. If I'm trying to take a copper pipe and use it as an electrode inside of a CO2 laser, which works at 10 microns, I can get away with any old metal polish to make it smooth. As long as it's smooth and shiny, roughly in the visible, it'll be flat as you can be at 10 microns, 10 times the visible. Okay? And then if I get up to a gigahertz signal, or hundreds of megahertz signal, I could probably get away with a screen, or even one thing that they use under antennas in the field that are very a great mirror is they'll take one of those hurricane fences, the metal fences that are rectangular holes that are mostly holes and just a little bit of wire. They'll throw that on the ground underneath the antenna and ground it if they need a ground there, or float it if not, and grass can grow up around it. Grass can grow up around it, and you never even see that the hurricane fence is lying on the ground, working like a beautiful mirror against the antenna that rises above it. If your wavelength is long enough, okay. Where so that's an example of what kind of a discontinuity you might be thinking about. A hurricane fence is basically transparent in the visible because you can see through it, right? In the visible. In fact, if you won't even notice, if you look at it, you won't even notice the wire. The wire. You have to focus on the wire to see the wire, right? So if it's just sitting there, you can see right through it. Whereas if you send an RF signal against it, it'll bounce off. It'll bounce off. Okay. So this discontinuity, I want to remind you of the other time we looked at discontinuities, which gave us boundary conditions. And we had N cross E1 and E2. E1 is the field here, and E2 is the field here. And what was this in plain English? What did that mean, that N cross E1 minus E2 equals 0? The tangential component. So the normal component is going to stick out something like that. And if I cross N with the field, I'm going to get the one that lines up with the surface. And the one that lines up with the surface is the tangential component. So that's E tangential 1 is equal to E tangential 2. Okay? We had a similar expression for H1 minus H2. And what did that equal? J. Very, very good. The surface current. The current on the surface. So in the same way that in Maxwell's equations, J produces an H, well, the surface current here can change the value of H across the boundary in the tangential direction. If we dot this with the field, and here I'm dotting it with a magnetic field, then we'll see what happens with the normal component of the field. And For the magnetic field, because of Maxwell's equations, we have the normal component being conserved across the boundary. So B normal 1 is equal to B normal 2. The rho in div D equals rho term changes that slightly. So the right-hand side of this is going to be the source term from the charge that's sitting on the surface. Okay. Now, out here we have the wave equation in material 1, and in here we have the wave equation in material 2. Okay. So the way we're going to approach the problem is we're going to solve the wave equation in material 1 We're going to solve the wave equation in material 1 There's the vector wave equation for the electric field, for example. You may have already derived that for the magnetic field. So you look at all the components of each one, and you get solutions. The solution we're going to play with would be a plane wave, one term of a Fourier series that represents any field that will bounce against the surface. And we'll solve that in material 1 for a K1 and in material 2 for a K2. Frequency will stay the same. So we'll have plane wave solutions here and plane wave solutions here. The amplitude and maybe the phase and maybe the direction changes. And so we'll figure out what happens to the solutions across that discontinuity in accordance with these boundary conditions. Okay? Now, one thing I wanted to point out, remind you of what we did last time at the very end, was we looked at the charge in the field inside of a conductor. Right? And so we worked with Maxwell's equations, and we derived, strangely enough, an ordinary differential equation in time for the charge distribution. There was a function that where the time coefficient was epsilon over sigma, the Debye time. And so the solution for that was an exponential decay with the remarkable spread in that time constant. But the lesson being the same, as long as I have some sort of conductivity, any charge that happens to be in that conducting surface will migrate to the surface. Any charge that happens to be in that conducting material will find its way to the surface of the material. It might take 3 attoseconds, it might take a little over a month, but it will get there. Okay? Once it's on the surface, if it has a reasonable conductivity, silicon or a metal, semiconductor or a metal, then it will produce a current. Okay? So if I have any kind of a conductivity in material 2, for example, or material 1, then what I'll have is I will certainly have a charge and moving charge on that surface. Okay? If I have an insulator, I might have charge, but it probably won't move. And it probably won't move in time to the wave. Okay? So even if an attosecond is much, 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 much faster than a gigahertz or even 100 terahertz. And so those electrons will track the field very, very, very well in a conductor. However, in an insulator, there may be charge there, but it won't move very much. It can't move. Okay? So those are some of the comments, some of the background that might inform our assumptions in our mathematics. So I'm going to do a couple of different cases for you, and just to show you how the boundary conditions work to fill out the field of the plane waves. And our first case is a plane wave, reflection, perfect conductor, normal incidence. Okay? So, z equals 0. Here I'll have a perfect conductor. So that sigma is equal to infinity. And if that's the case, my E will equal 0. My H will equal 0 in material 2. And on the surface, I'll have a rho surface and a J surface on the surface of that boundary. Okay? So the field here will be 0, 0, 0, all the way up to just the epsilon, close to the just a small squidgen away from that surface. So normal incidence means that the wave is propagating in the z direction, and the surface here is sitting in the xy plane. Okay, so it's coming out and it's going this way. So that's the boundary that we're going to be launching or throwing our plane wave against. Okay. Now, solving the Maxwell's wave equations, solving the wave equation in this area gives me an electric field with an amplitude propagating in the positive z direction. Okay? I've subscripted this electric field that moves in the positive z direction by I, which stands for incident. So this is the incident electric field perpendicular to the surface. Notice what a tight constraint I have. That z here is exactly the z of the normal of the vector. There's no misalignment at all, which is pretty weird to do because I have this metal surface and I've got this electric field, and they only know each other by this encounter. So I would have had to work very, very hard to tune my antenna or shine my flashlight so that it is exactly normal to the shiny metal surface that I'm illuminating. Okay? We'll get to a more generalized approach later on, but it's good to remark just how idealized this situation is. Okay? Well, we kind of know what happens when we shine light on a shiny metal surface, or we shine an electric field or shine a plane wave on a shiny metal surface. It reflects back to us, right? I mean, you can take out your cell phones now and hold it up against a piece of glass or something, and you'll see the reflection off of it. So you know that there's some reflection that comes back, and it's sufficient to write a reflected field, a reflected wave, that has a potentially different amplitude, that's moving in the negative z direction. That's moving e to the positive ikz, which is a wave traveling in this direction. Now, one last word about the plane wave and the plane interface. Okay? There's two planes, P-L-A-N-E-S, in this problem. There's the plane wave that's moving in the positive z direction. And remember, the reason we call it a plane wave is that its amplitude at any instant of time doesn't change with x and y. Okay? And similarly, this metal surface is also an infinite plane, an infinite superconducting plane. And so there seems to be a really nice match between the phase front of the plane wave and the boundary of the discontinuity. Okay? And that's not an accident in this sort of problem, in this sort of toy problem. Okay? And furthermore, if the plane wave has an edge, or the metal surface has an edge, which it most assuredly will, we're not going to treat what happens at that edge. We're going to be far away from that edge. Okay? We'll get a better sense of this as we move down the pike, particularly into antennas. All right, so we have to use our boundary conditions to find out what the relationship between ER prime and EI is. In other words, we have the solutions, we have the form of the solutions, but we have a few things that we don't quite know. Okay? And one thing we don't know is the relative amplitude of these things. Okay? So, here's what happens with the normal component of the electric field. There's an epsilon 1 in there, but that's not really even a big problem here. Is there a normal component to the electric field here? The normal component is pointing out in this direction. Is there a normal component to that electric field? No. Why not? By definition of the plane wave. The plane wave moves in the z direction, therefore its points, its polarization, is in the x direction or the y direction. And both of those are tangential to the surface. There's no z component, there's no normal component to that. So E normal is equal to 0. And I also know that E tangential 1 is equal to E tangential 2. That's by this boundary condition here. So I'm looking at the electric field, and I'm looking at my two boundary conditions for my electric field, and this is the one that matters. E tangential 1 is equal to E tangential 2. This, remember, is material 1. This is material 2. What is E tangential 2? Pardon? 0. Because there's no charge, no field, anywhere in this material. Right up to the edge here. So E tangential 2 is equal to 0 because sigma is equal to infinity. E tangential 1 and I care about this at z equal to 0, right at the edge, is equal to the total electric field at z equal to 0. And the total electric field at z equal to 0 is the incident wave evaluated at z equals 0 plus the reflected wave evaluated at z equals 0. So this is equal to incident plus the reflected. Well, I told you I chose an easy case when I set z equal to 0, because e to the 0 is 0, e to the 0 is 1, and e to the 0 here is, e to the positive 0 is 1. So this is just equal to E incident plus E reflective, and that has to equal 0 by the boundary conditions. And what that implies is that E reflected is equal to minus E incident. So there's an electric field that points, whenever the electric field is pointing in the x direction on incident, it points in the reflected wave points in the minus x direction. Okay? So the fields add up together linearly to cancel each other out to match up with the boundary conditions. So physically, one of two things is happening. Okay, both are correct. But we can look at this minus sign in two different ways. One is that there's an instantaneous flip in the direction of the electric field from incident to reflection. Okay? So the direction somehow flips instantaneously. The other way we can look at that is that there's a phase shift. There's a 90-degree phase shift that flips, a phase shift that flips you from positive to minus. That's a 180-degree phase shift, right? That flips you from positive to negative. So we can interpret that either as a direction flip, or we can interpret that as a phase shift. Okay? So either is sufficient. So here's my total field at all points in Z. I know something about ER. It's equal to minus EI. If I factor that out, I get an e to the minus ikz and a minus e to the positive ikz. And if I remember my Euler's relationships, I can write that as the sine of kz. If I put back in the time dependence, the real part allows me to check my phase. And if EI is real, then I get a sine of kz and a sine of omega t. And if I plot this, at omega t equal to 0, I get a line that looks like that. at omega t equals pi over 4. I get the sinusoid that looks like that. At omega t equal to pi over 2, 90 degrees. I get that. 3 pi over 4, I get that. Pi, I get that. So on down and so forth. Interesting to note that one nice thing to note is I always satisfy boundary conditions right at the metal surface. And I also satisfy electric field equal to 0 every half wavelength away from that. So the wave going this way completely cancels with the wave going this way at these points. Okay? So you might call those nodes. Okay? And that's what's going on with the electric field. So, one way I like to think about this, one way I like to figure this out is to take a look at the electric field that's going into the surface. So I might have an electric field that comes up like this. Okay? And E cross H into the screen tells me where my H is. Okay? So from there I know that H sits out over here. That's H incident. If I look on reflection, I know that at the boundary, EI goes minus. So what pointed up now points down. So there's a reversal in direction. And there's a reversal so this flips, and this vector flips. Okay? So now, if I do my E cross H, my reflected magnetic field is exactly the same. Okay? So two shifts get me back to the same answer. So the direction of reversal and the direction of propagation can be looked at 180 degree phase shift, plus another 180 degree phase shift for the return, for the flip of that, which adds up to 360 degrees or no change whatsoever when I consider the cyclic nature or the periodic nature of the fields. Okay? So I don't need I don't need to do anything with my magnetic field. Okay? So I can write the total electric field anywhere in Z is HI e to the IKZ, e to the minus IKZ plus H reflected e to the positive IKZ. And I know HI is equal to HR. So H total is equal to twice HI times the cosine of KZ from the Euler's relationship. Now, there was a relationship that we derived between the E and the H. Remember, we solved for the plane wave, and we substituted in for the H field, and we found a relationship between E naught and H naught that went in terms of mu and epsilon, which was we defined as the impedance. Free space, that was 377 ohms, right? Okay. So I can further write this as twice E incident over eta times cosine of kz. And the nice thing about that is I only have to specify one quantity, right? I can either measure the electric field or I can measure the power, and I can convert it back to an electric field or a magnetic field. Okay? So the power of this signal is characterized by one number regardless. Okay? If I put back in the time dependence and work through the real part, I get a cosine kz and a cosine omega t. And now, at omega t equal to 0, I get maximal. At z equals 0, I get 1. So I have a magnitude up here. At omega t equals pi over 4, this amplitude drops down, still goes through 0 here and there. And at omega t equal to pi over 2, I get the flat line. So here's H total, and the red is E total. Okay. And it's noteworthy that where H is 0, those nodes, it's all E. And where E is 0, it's all H. Okay. Now, I want to look at this a little bit more carefully. Okay? I want to look at that a little bit more carefully. We do have a boundary condition. We do have a boundary condition. And that boundary condition for H goes with the surface current. H2 is equal to 0. Superconductor, no fields, no charge, no moving charge, no electric field, no magnetic field. And so N crossed with H1 must equal J sub S. So H total I'll put the X in the I'll put the E in the X direction, and I'll put the H in the Y direction. The N is minus AZ. So N cross with this H total so X, Y, Z. Z, Y is minus X. There's a minus sign there. So we know what the surface current is. So we know that there must be a surface current, and we know the magnitude of the surface current, and we know the direction of the surface current. Now, one of the ways I look at this is, and you can decide where things start and where things stop, but the way I look at it is the magnetic field kicks up the current. So the magnetic field comes onto the surface. It kicks up the current. It kicks up the current in accordance with this cross product. And so the current that's generated is perpendicular along the surface to the magnetic field. But that's parallel to the electric field. And so that current that's moving in is slightly out of phase, 90 degrees out of phase with the magnetic field. I'm sorry, it's 180 degrees out of phase with the magnetic field, and then it's in phase with the electric field, and that's what produces the reflected electric field. And that also, if you think of it that way, and you don't have to, if you think of it that way, that accounts for that 180 degree phase shift. Is it takes a transit time, it takes a phase shift to generate the current, and then for the current to re-radiate back into the electric field. Okay? So if you're looking for a physical reasoning for why the electric field has that discontinuity, that sudden flip, well, you could, if you wanted to, if it makes you feel good, talk about that in terms of exciting a current and that current re-radiating back out as at the for the electric field. Okay, so there's all this charge on the surface. You kick it up, it starts oscillating. It becomes an antenna that radiates back out the electric field. Okay, that's sort of logic in hindsight from the mathematics, and again, some of you that'll make you feel good, and others it won't, but that's okay because that's the way intuition works. You look at people look at equations in different ways, and they see different things. But I just offer that as solace to some of you who were so bummed out about the lack of explanation of the flip of the electric field, just from the silly old boundary condition that we used to apply it, to derive it. Okay? All right. So that's one little thought on this. Another thought comes from the power flow. And remember that the S, the Poynting vector, is proportional to the electric field squared. Let me flip that back and for our plane wave solution, we found the time average Poynting vector, and we saw that it was proportional to E squared. Okay? So the Poynting vector is proportional to E squared. S incident is proportional to EI squared. S reflected must also be proportional to E reflected squared. E incident is equal to E reflected. Similarly, when I square them. And so what that suggests is that S incident has to equal S reflected. So if sigma is equal to infinity, there's no loss. If sigma is equal to infinity, there's no loss. Superconductor, perfect conductor. The power that hits the surface has to go somewhere. It's not going into the surface. It's not going into the material. No fields are allowed. So it's got to come right back out at you. Okay? And so if you're looking for another reason for this reflected wave, the source of this reflected wave, conservation of power demands reflection. Okay. Now, there's one other kind of cute trick that we can play with these with this treatment. Remember, we talked about forces, and forces. There was charges involved, moving charges involved, electric fields and magnetic fields. So in this problem that we're working, we've got electric fields, we've got magnetic fields, and we've got charges and moving charges. So we might as well pick up this equation and kick it around a little bit and see what it does for us, just for fun. So the right-hand side of this, there's going to be no term here because there's no electric field on the surface. The magnetic field, however, sees a surface current, or drives a surface current, depending on how you want to look at that. And that surface current points in the x direction. And the B field, multiply by mu to get the B field, Multiply h by mu to get the B field. Points in the y direction. So x crossed with y gives me z, so that there's a force F sub z, A sub z. Okay? It's potentially a force A sub z, F sub z, and it points onto the surface of the metal. Can you see that? So 2ei over eta, cosine kz, cosine omega t, a sub x. That's my j sub s. That's my current that we've derived. And the h field, 2 mu naught e sub x, e sub I over eta, cosine of kz, cosine of omega t. And if I multiply all that together, those cosine terms square. The ei over eta, ei squared over eta, is written as an s. The kz term is sort of spurious because we're at z equals 0. So this term is just 1. And so I have a cosine squared of omega t. If I play around with this mu naught and this eta, eta has epsilon and mu in there as well. And so the mu is in there. And that turns that into a 4 over c times the power density, power watts per meter squared, times the cosine squared of omega t. Okay? Now, the cosine squared is interesting because that means that I can look at the time average of f sub z. So I want to integrate this cosine squared over a period or over a very, very, very long time. And to do that integral, I'll use my trig identity. So the cosine squared is a half plus a 1/2 cosine of twice omega t. That's familiar. The cosine squared term gives you a DC term and then a harmonic. This guy goes to 0. Because it spends half of its time above the axis and half of its time below the axis. If you don't buy that argument, it's a trivial integral to do, and just goes to 0. And what's startling is that I'm actually left with something. I'm actually left with something. Now, I've been calling this a force, but if I'm careful about my units, watts per meter squared, meters per second, joules per meter squared meters. Watts times second is a joule. And that's equal to a Newton meter. Meter squared, meter, those guys cancel. So really, that's really what we've been talking about. A force is actually a pressure per area. Okay? Now, this is what we've done is we've derived this purely classically, right? This is purely classically. But the term of art for this is called a photon pressure. And the quantum understanding of this is a photon comes in, kicks against the metal surface, and comes back out. And that transfer of momentum gives rise to a pressure. Photons are interesting because they have no mass, but they move at the speed of light, and so those cancel out to give you actually a momentum of a massless particle. Okay. Momentum, I think I mentioned last time, is Planck's constant times k, h bar times k. It's the magnitude of that. But this is kind of an interesting effect. Okay. Now, let's see what it's worth. So let's take a laser beam, and let's take a megawatt per centimeter squared laser beam. And this is a pretty major laser beam. I mean, it's easy to make this laser, done all the time, but this laser will when focused down, cut through metal. This laser will burn through your hand. This laser is a pretty serious, powerful laser. But it's not. So it's pretty big, but it's not atypical. This is not what's going on at Lawrence Livermore to ignite, fusion or anything like that. Okay. We have some units to clean up. 10 to the 6th watts per centimeter squared. There's 100 centimeters per every meter. I have to square that. So that's 10 to the 10th watts per meter squared. Equivalent of 10 to the 10th watts per meter squared. That's pretty big. The electric field. In free space, multiply through by eta, 10 to the 10th. And that's something on the lines with 2 times 10 to the 6th volts per meter. So a couple megavolts per meter. Okay? A couple megavolts per meter. So how many 9-volt batteries? 1,000 or so connected up to give you that kind of a field. So again, this is not outrageously big or outrageously small, but this is a pretty hefty thing. So the pressure in the z direction, 2 times 10 to the 10th watts per meter squared. Now this is really where we see what's going on. There's a c in the denominator. And c is a huge number. So the power in the beam is fighting that c. So if I do this 3 times 10 to the 8th meters per second, I get something like 67 pascals. 67 or of something sounds pretty good, right? So how do I compare? What do we know about pascals? Pardon? Well, it's pressure, right? And so we're on the Earth, and we're under atmosphere, right? We're being constantly bombarded with nitrogen and other trace gas elements that are pounding against our bodies with a pressure, right? So we call that 1 atmosphere. Does anyone remember how many pascals take up an atmosphere? You'll remember the number when you see it. Anyone brave enough to? Anyone want to take a guess? All right. I think you've seen this number before. 101 kilopascals. Okay? That's what we face right now, right here in this class, is 100,000 pascals pounding against our body. Right? Anybody feeling any worse for that? Maybe after the end of a long day or a seemingly long lecture. Right? But compare that 100,000 to 67 pascals. Tiny. And I guarantee you if I shine this laser on you, you would feel it. Right? Different interaction, of course. But a pretty large field gives rise to a tiny, tiny, tiny photon pressure. So this is most engineering problems. This is a nicety. This is an interesting classical, or quantum mechanical, depending on your persuasion, effect. Okay. But people have talked about trying to harness this, and one of the things that always keeps coming up is if you have a nice perfectly conducting sheet that's pretty light, you can erect it and you can unfurl it in space where there is no pressure, but there is light from the sun, and so you could sort of build a space sailboat. Where you're out there, you unfurl your few kilometers squared of mylar sheet, you rig it towards the sun, and it starts off really slowly. But F equals ma, so as long as there's an acceleration, eventually, without power, without any fuel cell, without any propulsion, eventually, if you read enough books, you'll get to Mars. So that's one of those kind of almost science fiction, almost plausible kinds of scenarios that come out of this effect. Okay. Let's see. I think I have time to do one more calculation for you, and let me just dial it down a little bit. So we have a conductivity that's infinity. So let me just consider real quickly the case of a finite conductivity. And remember, we solved for that, and the field distribution becomes exponentially damped, and exponentially damped in a skin depth delta. Do you remember that problem? Was it only last time that we did that? Propagation of a field in a lossy material. So we know in material 2 what the field solution is, and there's a power that's dissipated per area, because this is always a plane wave, it's infinite extent, so you have to normalize somewhere. And this power dissipation comes from the Poynting Theorem, Do you remember we did that really beautiful theorem a couple weeks into class where we developed E cross H in the Poynting Theorem? We had an L term, a C term, and an R term. And this is really coarse, and it's almost embarrassing. But what I'm doing is I'm taking E times J, and then I'm saying, okay, well, I want to integrate over a volume, or over a length, and I don't really feel like doing that exponential, so I'm going to do 1/2 base times height. Okay? So I'm really being just trying to get an order of magnitude here. So I'm just fitting that exponential as a triangle, 1/2 base times height. The electric field is equal to J over sigma, and the delta and the skin depth is twice over sigma omega mu. So the dissipated power is 1/2 J squared over the conductivity times the delta function. J is Js over the delta function, which is equal to the incident electric field over the delta function, the skin depth. And that's equal to E incident over the eta times the delta, the skin depth. And if I put all that stuff back in, I get the dissipation per area, 1/2 EI squared over the conductivity times epsilon naught over mu naught inverted times the square root of sigma omega mu over 2. Just collecting all these material constants. And that's equal to epsilon E squared, square root of omega over 8 sigma mu. Okay? So if you look at what comes back to you with a finite conductivity, you have a small loss, and you can calculate the degradation of your nodes of your reflected wave by a small reflectivity constant. Okay, and we'll see how to do that in next time when we look at normal incidence on a perfect dielectric, so conductivity equal to 0.